Okay, so I want you to try and imagine something for me. Imagine the sheer difficulty of threading a needle. It requires intense focus, super steady hands, and absolutely perfect alignment, right? Well, now imagine trying to thread that exact same needle, but you and the needle are both flying at thousands of miles per hour in the absolute pitch-black vacuum of space. That mind-bending level of precision is exactly what we're going to explore in today's explainer. Welcome to a deep dive into India's SpaDeX mission, where we're unpacking the mechanics behind one of the most complex orbital maneuvers humanity has ever attempted, the cosmic handshake.
To really understand why this mission is such a game-changer, we have to start with a massive, big-picture question. How do you actually build a city or even a laboratory in the vacuum of space? Before humanity can construct sprawling space stations, send giant habitats to Mars, or retrieve precious lunar samples, we have to solve the ultimate orbital construction challenge. We can't just build massive, heavy structures on Earth and launch them all at once. Our rockets simply aren't big enough for that. So the reality is, we have to launch them in smaller pieces and assemble them up in orbit. And to pull that off, you need a totally flawless joining mechanism.
Well, that brings us to space docking. By definition, this is the process where two independent space objects, like spacecraft or satellites, come together and physically join for a specific purpose. Think of it as the ultimate prerequisite for all deep space infrastructure. If you can't dock safely, you can't share power, you can't transfer astronauts, and you definitely cannot build a space station. Mastering this incredibly high-stakes maneuver literally unlocks the entire future of space exploration.
So in this explainer, we're going to break this all down into 5 quick parts. We'll start with the Space Assembly Challenge, go inside the actual SpaDeX mission architecture, walk through that high-stakes docking sequence, look at how this fuels India's space future, and then we'll wrap up with a quick mission mastery revision.
All right, let's jump right into part 1, the Space Assembly Challenge, and the race for orbital construction.
4. That is a massive number here. Historically, every major spacefaring nation hits a wall when it comes to payload limits because Earth's gravity is just so unforgiving. The only way around that bottleneck is orbital construction. And with the success of this mission, India has become only the 4th nation on the entire planet to unlock and master this capability. This isn't just some neat science experiment, you guys. It represents a fundamental shift in global space dynamics. It essentially signals that India isn't just launching satellites anymore, they're now fully capable of building permanent, complex infrastructure in orbit.
Moving on to part 2, let's actually go inside the SpaDeX mission and meet our orbital dancers.
So the Space Docking Experiment, or SpaDeX for short, launched on December 30th, 2024, riding on the trusted PSLV-60 rocket, and the actual docking took place a couple of weeks later on January 16th. Now, a mission like this requires 2 highly specialized partners. First up, we have the Chaser, officially known as SDX-01. Its job is the active one. It has to dynamically approach, align, and interact. On the flip side is the Target, SDX-02. The Target's main job is just to be a stable, reliable docking point. So they launch together, but to actually succeed, they have to separate and operate as 2 completely independent entities executing this highly choreographed dance. And because we're talking about building in space modularly, the scientific tools are actually split up. Spacecraft A carries a high-resolution camera, which is super crucial for visual alignment. Spacecraft B, on the other hand, carries miniature, multispectral, and radiation monitor payloads. This is a brilliant way to show how multiple capabilities can be distributed. By separating the payloads like this, the mission proves that specialized modules can be launched completely separately and then snapped together to create a fully functional space laboratory.
Now, obviously, bringing 2 massive objects together at orbital speeds, that is incredibly dangerous. If they bump even a little too hard, they could shatter. So, to prevent a catastrophic collision, these spacecraft rely on a breathtaking array of advanced tech. We're talking laser rangefinders and rendezvous sensors for pinpoint millimeter accuracy. They also use these robust attitude and orbit control systems, powered by reaction wheels, magnetometers, and thrusters, to continuously fire micro-adjustments and keep the satellites perfectly oriented in 3D space.
Okay, part 3, the high-stakes docking sequence. This is where we actually thread the needle.
It's really important to build the right mental model here. Docking is not just one quick click and you're done. It's a carefully planned, multi-stage mechanical system. The whole procedure is broken down into 3 main stages. First is distance reduction, where the chaser systematically shrinks the gap. Second is the docking mechanism phase. This is where extended rings on both satellites physically connect, and a motor-driven capture sequence actually pulls them in and rigidizes the connection so it becomes completely unyielding. Finally, we hit integration and testing, where the true magic happens: power sharing and unified control. Let's visualize that first stage, the approach phase, because the precision required here is just staggering. The chaser doesn't just zoom straight in. It holds its specific waypoints. First, it stops at 500 meters to double-check its alignment. Then it carefully moves into 225 meters, then to a seriously nail-biting 15 meters. Finally, it inches its way to a mere 3 meters before it actually initiates the capture. Literally every single stage is a critical go or no-go decision.
And here is the absolute coolest part. Once that physical connection is rigidized, the two previously independent objects undergo a complete systemic merge. They start sharing power. Their computers completely sync up. Synchronized control commands are issued to the combined structure as if both satellites were now just a single, unified entity. So they no longer fly as a chaser and a target. They fly as one integrated machine.
And the immediate payoff for all this? 2 years. By successfully sharing power and merging their controls, the operational life of these newly joined spacecraft is extended for up to 2 full years post-docking. This proves for sure that we can refuel, recharge, and revive aging satellites right there in orbit. It's a total game changer, transforming space from a disposable environment into a sustainable one.
Which brings us to Part 4, Fueling India's Space Future and the larger strategic impact.
So let's answer the so what question. Why does this matter so much today? Well, look ahead to the year 2028. That's the scheduled launch for the Bhartiya Antariksha Station. Like we said earlier, you literally cannot launch an entire space station on one rocket. You have to launch the living quarters, the power arrays, and the science labs separately. The assembly of this 2028 station relies fundamentally on the exact docking technology proven by SpaDeX. Without this cosmic handshake, the space station is just a drawing on a whiteboard. With it, it becomes reality.
But wait, it doesn't stop in Earth orbit. Let's talk about the Moon. The upcoming Chandrayaan-4 mission aims to do something extremely difficult: retrieve lunar samples and bring them all the way back to Earth. To pull that off, a module has to launch from the lunar surface, rendezvous with a transfer module waiting in lunar orbit, and dock seamlessly to transfer that precious cargo. SpaDeX is the critical link that guarantees we can actually bring pieces of the Moon back home.
All right, let's bring it all home with Part 5, our Mission Mastery Final Revision, highlighting the key takeaways.
We've covered a ton of complex ground today, so let's rapid-fire this so it sticks in your mental framework. Here are your 5 must-remember takeaways. 1. India is now the 4th nation globally to master orbital docking. 2. The mission launched aboard the PSLV C-60 in December 2024. 3. It relied on this intricate dance between the active chaser SDX-01 and the stable target SDX-02. 4. Successful docking allows for power sharing that creates a 2-year merged operational lifespan. And 5. This tech is absolutely vital for the 2028 space station and the Chandrayaan-4 lunar mission.
We started all of this by imagining threading a needle in the dark at thousands of miles an hour. Humanity and India's space program has just proven it can thread that needle flawlessly. But this leaves us with a really fascinating, provocative thought. If we can now modularly assemble, refuel, and integrate heavy structures dynamically right there in orbit, with the docking puzzle finally solved, what truly limits how far and how large we can build into the cosmos? Keep that question in mind as you watch the skies over the next few years. Thanks for joining me on this explainer, and keep learning.